and welcome to the 7 secrets of maintainable codebases. This session kind of grew out of my experience of analyzing large-scale codebases, because as part of my day job, I've analyzed hundreds of different codebases. And there are some patterns that I see recur over and over again, and those patterns are independent of programming language or technology. So today, I'm going to try to share some of my observations with you. And I want to do this in a different way, because I'm pretty convinced that we, as an industry, we know what good code looks like. We all know about the importance of naming, testability, cohesion, the solid principles, and all that other stuff that we think is important. So today, I want to go beyond that. And my starting point is going to be data analysis. Why data analysis? Well, because data analysis is mainstream these days. It's something we use on a daily basis. And the rise of machine learning has taught us how to find patterns in complex phenomena. And it's we developers that do that job. What's interesting, though, is that we as developers have never taken those techniques and turned them on ourselves. To uncover patterns in our own ways of working, to see patterns in how our systems evolve and grow. So that's what I want to do today. I want to show you how we can find patterns in behavioral data of us as software developers and see how that information helps us make better decisions. Decisions that takes us towards maintainable code bases. And in order to do that, we obviously need some kind of behavioral data. How can we get that? The good news are you already have all the data you need. We're just not used to think about it that way. I'm talking about our version control systems. Our version control system is basically a perfect behavioral log of how we as developers have interacted with that code base. And we also have a really nice timeline in it. So let's uncover the secrets of version control data, and let's jump right in to my first observation. Because I've found that maintainable code goes way beyond technology. And we as developers, we tend to be pretty good at the technical side, but I've seen that we often miss the social implications of our designs. And this is important. Here's why. This is what pretty much every system looks like these days. We have a bunch of different components that we somehow integrate and let them exchange information, and we have one or more big databases. Now, each one of those subsystems or components can be fairly large. They can consist of hundreds of thousands, sometimes even a million lines of code. And the scale of that alone makes it virtually impossible to reason about. In addition, remember, code is a moving target. It changes all the time. But we have more challenges than just pure scale, because today's systems tend to be developed in multiple different programming languages. And of course, they're also developed by multiple programmers organized into multiple teams. And this leaves everyone with their own view of how the system looks. No one has a holistic picture. But this is not just a technical challenge, because I have found that systems that look like this tend to come with an organization that looks like that. So our challenge as developers is to somehow balance these technical and social complexities. And this is indeed a hard problem, but it's a problem that we can simplify by understanding my next secret here. Because I have found that when it comes to maintainable code, all code is equal, but some code is more equal than others. And in order to explain what I mean about that, we need to take a different view on our code base. We need to take an evolutionary view. Here's our starting point. Please have a look at the following graphs. Each one of them shows exactly the same thing. On the x-axis, you have each file in your system. And those files are sorted according to the change frequency, which is the number of commits. How many times have you made a change to that particular file? And the number of commits is what you see here on the y-axis. Now, what I find so fascinating about this is that the examples I show you are from 3 radically different systems, developed in different programming languages, targeting different technologies. They're developed by different organizations, different developers, and they show a different lifetime span. Yet, do you see any common pattern? They all show exactly the same distribution. They show a power law pattern. And this is something that I've found in every single code base that I've analyzed. This seems to be the way that software grows. And what this means to you is that in your typical code base, most of your work tends to be in a fairly small part of the code. Most of your code tends to be here in the long tail, which means it's code that's rarely, if ever, touched. And this is important because it gives us a tool to prioritize. If we have this information, we can use it to our advantage and target improvements to the parts of the code where we actually work the most, the parts that matter the most to us. And this simplifies the problem a lot. But we need to do even better. And I would like to show you how. But in order to do that, I need to take a risk. I need to put up a slide. And I'm pretty sure that this is the point in the presentation where you will all vehemently disagree with me. But I need to take that risk. We cannot let that stand back for the truth. Because I have found that when it comes to maintainable code, code complexity isn't the problem. We developers, we are so conditioned to despise bad code. We have learned that we need to refactor and improve bad code as we see it. And we have been taught that that's the fastest way forward. The problem I have with that, it's just not true. And the graphs on the previous page kind of indicates why that's the case. All code isn't equal. But still, we cannot discard complexity entirely. We just need to find out when it matters and when it doesn't. And this is a problem I've been struggling with for years. So please let me share a little story with you. This is something that happened 5 or 6 years ago, back in my old life as a consultant. And I worked on a fairly large project. And on that project, we had a problem that I'm pretty sure none of you have ever experienced. It was kind of crazy. But believe it or not, management thought it took way too long to add new features to the system. Yeah, you never heard about that. So my task was to try to do something about that. So what I did was that I took a bunch of tools that were able to calculate something called code complexity. So we have a bunch of different complexity metrics, right? So I basically took this tool, I threw it at the code base, and out came a prioritized list of every module in the system, and each module was assigned a complexity metric. Now, the interesting thing here was that there was a clear #1 candidate. There was one module in particular that was way off than the rest of the code. So there's one part of the code that were much more complicated. The interesting thing, however, was that when we started to investigate that finding, it turned out that that part of the code had been stable for 3 years. It worked wonderfully in production. It just did its job, and we never had to touch it. Is that really the right part to start to focus improvements on? What can we expect to gain by that? If you ask me, absolutely nothing. To me, it's just a big risk. And besides, we probably have much more urgent matters to attend to. So how can we find that part of the code that really matters? At the same time that I worked on this project, I was in the middle of my psychology studies at the university, and I took a course in forensic psychology. Now, I think that forensics in general has a lot to offer to us software developers. The mindset is just right. But there's one technique in particular that I want to share with you. This is a technique called geographical offender profiling. And geographical offender profiling is something forensic psychologists use to track down serial offenders. So let me show you how it works. We've already seen some maps today. Here's another one. This is a map over London. And you see a number of green dots here, right? Each one of those dots represents a crime scene. We have 56 different crime scenes here. 56 crime scenes that we managed to link to the same offender. How do we know it's the same offender? Well, we may have hard evidence like DNA or fingerprints, or maybe it's just the same modus operandi, the same method of operation used by the criminal, so we know it's the same person behind all those crimes. The next thing we do in our geographical offender profile is that we take all those crimes their geographical distribution, and weight it together. But we also add our knowledge of human psychology and human behavior into that weighting, so it's part mathematical and part of psychological weighting. Now, when we do that, we're able to calculate a probability surface that we can project onto our geography. And using that probability surface, we're able to predict the most probable home location of the offender. And that's the red area here in the top of the map. That's something forensic psychologists call a hotspot. And according to the research, there's a 70% chance our offender will have his home base there. Now, a question. Why am I telling you all this stuff? How does it relate to software? Well, let me tell you. Let's take a step back here and look at what we have actually done. We have taken a potentially vast geographical area and narrowed it down to a much, much smaller part. A much smaller part where we can now focus our manual efforts and human expertise and still be pretty sure that we get what we want. So what if we could do the same in code? What if we could take those million lines of code and narrow them down to just a few hotspots? Let's see how we can do this in code. Here's a geographical offender profile of a software system. So what you see here is approximately 300,000 lines of code. And I'm going to walk you through this visualization in a minute. This data is built up of behavioral data from software developers, from our version control data, in this case 2,400 commits. By identifying patterns in those commits, we're able to project a probability surface onto our code base. And using that probability surface, we can identify the most probable maintenance savings in that code. Now, before I walk you through this, I just want to point out that the hotspot analysis in code is actually a social analysis, because this visualization is made up from the contributions of all authors here. We have 67 authors that have been contributing code here. So you can basically view each commit that you do as a vote for the relative importance of that code. So a hotspot analysis is like the collective intelligence of all contributing programmers. Now, what you see here, if you focus on the large blue circles that you see, you will see that they have other large blue circles inside them. Each one of those circles represents a folder. So this is a hierarchical visualization that follows the folder structure of your code. It's also an interactive visualization, so you can click on one of those folders and zoom in on the details. And if you do that, you will see that each file is represented as a circle. And they have different size. So that's because we use size to represent the complexity of the underlying code. Now, how do you measure complexity? Well, we have a lot of different metrics in the software industry. And you can basically use any metric that you want, because what they all have in common is that they're equally bad. So I tend to use the simplest possible thing. I tend to use the number of lines of code, which is actually a fairly good proxy for code complexity. But this is not enough. In addition to this, we need to know, does this represent code that we actually need to work with or not? And this is data that we pull out of our version control system. So again, we look at the code change frequency here. And we use color to represent it. So the more red a piece of code, the more effort, the more commits we have spent on that part of the code. And the interesting thing is, of course, when we combine these two dimensions, because now we're able to identify complicated code that we also have to work with often. So I want to show you how a hotspot analysis looks on a real-world system. So this is a hotspot analysis I did quite recently on Microsoft's Roslyn project. Now, is anyone familiar with Roslyn? Oh, a lot of you, like 20, 30 people. Cool. So Roslyn is an interesting project because Roslyn is a compiler platform, and it actually implements two compilers itself. It implements the C# compiler in C# and the Visual Basic compiler in Visual Basic. So this is a polyglot code base. Now, if you look at the #1 hotspot in Roslyn right now, it's a file called command line tests written in C#. There's another top hotspot called command line test written in Visual Basic. Do you think there's some kind of relationship between those two files? I don't know. But in a few minutes, we're going to learn a technique that helps us answer that question. Before we go there, I want to point out that those hotspots, right, they look tiny here on screen. That's just because the scale of Roslyn. Roslyn is huge. What you see here is approximately 4 million lines of code. And each one of those hotspots represents a file with 7,000 lines of code. And here I would like to argue that if you have a file called command line tests that consists of 7,000 lines of code, perhaps that isn't a good unit of test. So what I would do in this case is that I would go into that file, try to identify the different responsibilities of the command line, things like parsing, validation, diagnostics, and I would split the file accordingly. And if I do a refactoring like that, not only will each part be easier to understand in isolation, the big win is that you get an entirely new context. Because if you follow up with another hotspot analysis at a later date, you will actually get feedback on what part of the solution you managed to stabilize and which parts that keep changing. So cohesion is something that helps us reason about the evolution of code. Another thing I want to point out is that you saw both of those hotspots. They were in a test code. And this is a pattern I see over and over again. The worst offenders tend to be test code. And I think the reason for that is because we developers, we tend to make a mental divide. On one hand, we have the application code, and we know it's vital. It's important that we keep it clean and nice and easy to evolve. On the other hand, we have the test code. And most of the time, we're happy if we get around to write any of it at all. And I think this is dangerous, because from a maintenance perspective, there's really no difference between application code and test code. So if your tests lack in quality, they will hold you back. All right, let's see what the hotspots brought us. We have already seen that by just looking at the change frequency of code, we can limit the amount of code we need to consider for improvements. When we add a complexity dimension, we can narrow it down even more. And I tend to find in most code bases that the top hotspots rarely make up more than 3% of the code. And this means that we can focus our improvements on a fairly small part of the code and still be pretty sure that we get a real effect in terms of both productivity and quality. And the reason I say quality is because hotspots tend to be pretty good predictors of defects. And the hotspots show you precisely which parts of the code base that actually matters. All right, I'm going to leave the hotspots now for a while. I will come back to them. But before I do that, I want to take a look at our primary tool as software developers. And no, I'm not talking about the compiler. I'm not talking about your IDE. I'm not talking about Emacs, not even Vim. I want to talk about your brain. Because I've found that our brain does not always work in our best interest. And I like to demonstrate that by taking a small poll here. Now, please, think back to the last large project you worked on, the project you're working on right now, perhaps. How many of you know where your hotspots are? A few hands. Please keep your hands up if you're 100% certain. There are some hands. Cool. So you may well be right. You know your code base better than I do. What I want you to keep in the back of your head, though, is that there's a strong body of psychological research that suggests that we humans can't really always trust our own judgment. And to show you why that may be the case, we need to talk about something else. Yeah, that's right. We need to talk about gorillas. So this is one of my favorite experiments in psychology. It's a fairly well-known experiment, so you may have heard about it. Now, what researchers did here was that they recorded a video. They recorded a video of two teams that played basketball with each other. And your task as a participant in this experiment was to sit down, watch that video, and count the number of passes between players on the same team. Now, as you sit down and watch that video, in the middle of the video, something interesting happens. A man dressed in a gorilla suit walks across the basketball field, stops right in front of the camera, turns towards you and starts to beat on his chest before he walks off. After you have seen that video, the experimenters will ask you, did you notice anything particular? And you will of course answer it, yeah, I mean, a man dressed in a gorilla suit, that's a little bit odd, isn't it? And of course, that's not what happened at all. It turned out that more than 50% of the participants failed to notice the gorilla. And this was a surprisingly high number, so the experiment was repeated, and this time they used some eye-tracking devices. And it turned out that the human mind is capable of missing the gorilla even when it's right in front of our eyes. Even when the image of the gorilla hits our retinas, we fail to see it. And the reason we fail to see it is because you don't see with your eyes. You see with your brain. And in order to perceive something, you need to focus your attention on it. But your attention was directed to count the number of passes between players on the same team. And the takeaway for me here is that if we humans are capable of missing something as obvious as a man dressed in a gorilla suit, what's the risk that we will miss the gorillas in our own code? And I actually think it goes deeper than that. Because the human brain has other ways to get us into trouble. So let me share another finding with you. This is something completely different. If you take part in this experiment, what will happen now is that the researchers will show you two pictures. Two pictures of two different faces. And your task is to select this you find the most attractive. So you make your choice, and the researchers hand you a copy of your choice. Only they don't. They trick you. So they actually swap the copies. And you receive a copy of the face that you didn't choose. And now they do something really, really evil. They ask you, could you please motivate your choice? Interesting situation. Let's think about that for a while. So we end up there with a copy of a photo that we didn't choose and are now asked to motivate a choice that we didn't do. And again, if that would happen to you, I'm pretty sure that you would notice that, no, that's not the photo I picked. But again, that's not what happened at all. In this case, more than 2/3 of the participants failed to notice the swap. And if you read the original research, I promise you, it's like comedy gold, because they include transcripts from some of the interviews where people motivate choices that they didn't do. So for example, I remember this woman, she says, yeah, I picked this photo because I just love these earrings. The photo that she actually picked don't show any earrings at all. And of course you have this stereotype, right? This overconfident man that says, yeah, I picked this photo because I really prefer blondes. The photo he actually shows a dark-haired woman. So everything else is an after-the-fact rationalization of a decision you never did. And these are two examples on cognitive biases on an individual level. But if you want to see a real bias situation, or kind of a bias disaster, please try the following experiment. Take a number of individuals, put them together, and call that a team. Let me show you what I mean. And to do that, we need to travel into something that may look a little bit unethical. But please relax, I promise I will keep this nice. So, how many of you have been given the advice that if you want to influence a meeting, you should speak first? 3, 4 people maybe. Cool. So in that context, it's actually good advice. Because the first person who speaks in a meeting will bias the whole discussion, will influence the whole direction of that discussion. But there's an even sneakier way to get what you want. And this is based on something called vocal minorities. And vocal minorities is the fact that we humans, when we hear our opinion repeated over and over again, we come to believe that that opinion is more popular and widespread than it actually is. And that's true even when it's the same person repeating the same opinion over and over again. Crazy, right? So if I want to manipulate you, all I have to do is to keep repeating stuff like, have you heard about Common Lisp? It's a fantastic programming language. Do you know Common Lisp? It's an amazing programming language. Now, I try to be a good person, so I will only manipulate you in a good direction. Common Lisp is indeed great. But let's say it was the other way around. Let's say that someone complains a lot. Have you seen that network module code? It's so crappy. Have you seen that network module code? It's pure crap. We need to throw it away and start over again. If you hear that opinion repeated over and over again, how do you think it may influence your sense of where your hotspots are? And the reason I tell you all this is because I really want to make the point for my next slide. Because do use your expertise, do use your intuition, and make sure to base your decisions upon data. And we have already seen how we can get some data that help us around the technical decisions of your code. Now I want to take it a step further and see how we can uncover change patterns over time in our code base and why that matters. So I want to show you how we can know your real change patterns in code. And I want to introduce this segment by talking about the cost of surprise. The reason I want to talk about surprise is because surprise is one of the most expensive things you can put into a software architecture. And there are different kinds of surprise. And I would like to show you the first kind of surprise by presenting what has to be my all-time favorite code. This code was part of the original Apollo mission. So this is the code that actually took us to the moon. How cool isn't that? So please, take a few seconds and have a look at this timeless beauty here. In particular, focus on the comments. Who wants to go to the moon on that code? So one could argue that this is likely to be a surprise to the end user. That's not the kind of surprise I want to talk about now. I want to talk about the surprise that we as developers leave behind for the poor maintenance programmer coming after us. And I want to show you how a technique called temporal coupling helps us uncover those expensive change patterns. So, has anyone heard about temporal coupling before? There are a few of you, great. So, temporal coupling is quite different from the way we typically talk about coupling. When we talk about coupling, we typically mean a dependency. Temporal coupling is different because it's not measured from code. Temporal coupling is measured from the evolution of your code. So temporal coupling is about different files that tend to change at the same time. Now, let me show you some specific examples. This is a case study I did on ASP.NET MVC. And if you worked with ASP.NET MVC, you know that they have been focusing a lot on automated tests. So, as a consequence, a lot of the temporal dependencies you will find is something like this, that you have a unit test that changes together with the unit under test. This is not surprising. This is exactly what I would expect. In fact, I would be quite worried if that dependency in time wasn't there. It would probably mean that your unit tests aren't being kept up to date. So I tend to ignore those cases, filter them away, and instead I focus on the cases of temporal coupling where I don't have any easy explanation. For example, this one. Inside ASP.NET, there are two classes. One is called a script tag helper, and the other one is called a link tag helper. And if you look at the code, you will see that there's no direct dependency between them. And yet, they keep changing together in 89% of all commits. And they've been doing that for more than a year. How could that possibly be? To answer that question, I need to look at the code. But today, I'm going to do it a little bit different. I'm going to delegate that responsibility to you. So what will happen now is that I will show you a copy of the script tag helper next to a link tag helper. And your task is to see if you can spot some kind of subtle patterns between them. Ready? All right, let's go. Script tag helper, link tag helper. Do you see some kind of subtle pattern? Yeah, that's right. A dear old friend of mine, copy-paste. And yeah, perhaps I'm a bit unfair here, because this is not really copy-paste, because they've done something very rare here. They actually updated the copy-pasted property names. And now, look carefully, because I promise you, you will never ever see this again. Believe it or not, they have updated the copy-pasted documentation. So no, this is not copy-paste. This is copy-paste with a gold plating. But I would still claim that they kind of model the same process, the same business flow, right? So this is actually a duplication of knowledge. This is a violation of the derive principle, the don't repeat yourself principle. So this is code that we actually want to refactor. So we want to get rid of this software clone, and the way we typically do it is we just extract our third class here that encapsulates the shared responsibilities, and our temporal coupling will go away. But we can do even more with temporal coupling. We can use temporal coupling to analyze complete software architectures. And I'd like to show you an example using microservices. Why microservices? Because right now, microservices are all the rage. And that just means that tomorrow's legacy systems are going to be microservices. So let's stay a step ahead here. This is what microservices look like in PowerPoint. In reality, they tend to look much more like this. So we have learned to avoid duplication. So we may extract some shared utilities for communication. We see similar database access patterns, so let's encapsulate them in a database utilities library. And of course, we want to follow that recommendation of providing a shared service template so that the services behave in the same way. And obviously, we want to make our services as easy to consume as possible, so let's introduce a client library to each one of them. Now, each one of those things may well be good. What we need to keep in the back of our head, though, is that in microservices, loose coupling is king. The moment we start to couple different services to each other, we lose most of the advantages of microservice architecture and are left with an excess mess of complexity. So if we have a fundamental architecture principle like loose coupling, why don't we supervise it using temporal coupling? And what I do in this case is I measure temporal coupling not on individual files, but on between services. So we group different files, measure temporal coupling on that. And we want to look out for patterns that violate our expectations. Something like this, where multiple services change together due to a shared dependency. Or even worse, when multiple services tend to change together like this, which suggests that they are not as independent as they should be. So temporal coupling used this way is a way to help us get an early warning so that we can react on time before we have introduced a really, really expensive surprise. All right. So far, I've been talking a lot about the technical challenges of maintaining large code bases. Now I want to move on to the social code bases. And I think this is an important part because I have found over and over again that organizational problems are often mistaken as technical issues. And we need to address this if we want to be able to write maintainable code. And I think the reason we fail to do that so often is because social information is something we cannot see in the code. It's just not visible there. So we need to change that. So let's take a social view of our code base. Here's a starting point. So this is an analysis that is called fractal figures. And it shows the fractal figures of the Closure project, the development of the programming language. Here's how it works. Each file is considered a box, and each programmer gets assigned a color, like this. And now, the more that programmer has contributed to that code, the larger the area of the box. So fractal figures is something I started to use as a communication tool to do onboarding and to facilitate communication and discussions. So let's say we want to join the Closure project, and we want to do a change over here to the module on the top called Evaluation. And we see that evaluation is written by Stuart Holloway. So if we have a question around evaluation, Stuart is probably the one to ask. And he can probably also review our work and give useful feedback. We also see that most of Closure is developed by this dark blue developer, which seems to be someone called Rich Hickey. So if we have a question about closure in general, Richiki may know a thing or two about it. But I will claim that the fractal figures are useful even without the color legend. And what I do in this case is that I look for patterns like this. And the reason I look for this is because both of these, they show radically different patterns, but both of those files show that they have been maintained by more than 20 different developers. And if this is something that occurs over and over again, that 20 different people need to coordinate their work in a single file, we may have a problem. And the reason I say we may have a problem is because the number of contributors to a file is one of the best predictors on the number of quality issues that file will have. And you have a reference here where you can read up a little bit on that finding. It's actually empirical research. And I also see that that pattern often leads us to believe that we have a technical problem with code quality or code that's hard to understand, when in reality it's a social problem. And the fractal figures, they also help us understand how software evolves. Because in my day job, I often come across old code bases. That is code that's been around for 10, 15 years. And what I tend to find in those code bases is that, again, most of the code is in the long tail. And most of the development action seems to be in some fairly large hotspots that are quite central to that system. So when I find something like that, I always look back in time, I look at the trend. And what I tend to find is that those hotspots have been problems for years. So why haven't we done anything about that code? Why hasn't anyone refactored that code? Do you know the reason why much existing code is never improved? The reason is because the code looks like this. The fractal figures looks like that. You have 20 further developers that work on the same parts of the code all the time. So you cannot just rewrite that code because you will destroy the work for 20 other people that try to contribute in the same time. So you need to use a different strategy. And I just want to point out that I find it quite ironic that the reason we cannot improve the code is because we are so many people working on it in parallel. And the reason we are so many people working on it in parallel is because we cannot improve the code. And I think the first step towards real improvement is to measure and understand what the actual problem is. All right, so this often leaves us in quite an unfortunate situation that I call immutable design. And trust me on this one, I'm a functional programmer, but in this case, there's nothing good with immutability at all. All right, now when we talk about knowledge, I want to talk a little bit about how we should turn an eye towards the blind spots in our code. And I want to do this by introducing you to Mr. Paul Phillips. Does anyone here code in Scala? Cool. So Paul Phillips wrote a lot of Scala code. He was the top contributor to Scala for 5 years, and he wrote a lot of the code there. Then, 3 years ago, Paul Phillips made this presentation where he announced his decision to step back and stop contributing to Scala. So I thought about that. What's the consequence of that? What's the consequence of a main developer that leaves a code base? That's something that happens all the time. So I decided to try to measure the knowledge loss in Scala due to Paul Phillips leaving. And this is an analysis I did 3 years after Paul Phillips left. So here's what I found. Have a look at those red areas in the Scala code. It's the same visualization we saw before, but now the red areas are no hotspots. No, they represent abandoned code. That is, code that's written by a developer who's no longer part of the organization. And this is something we can use to reason about the knowledge distribution. For example, we see there are a lot of red areas here in this quite central part. It's something called a compiler. Now, I don't know Scala, but it may be important. But you can, of course, also use this a little bit more proactively. And what you do in this case is that you look for patterns like this. We have an almost entirely abandoned subsystem. And if you find that pattern, use that information to your advantage. Use it, for example, as a risk mitigation, as part of your planning. So if you know that you need to add a new feature to an abandoned part of the code, use that knowledge to schedule some additional time for learning. because it is a hugely increased risk to modify code that we no longer understand. All right, I've arrived at my final point, and I think the next point is really a true secret because it's something we almost never talk about in the industry. Because I have found that in order to maintain a code base successfully, we need to make it fun. I work at a company called Ampere, and we develop all our stuff in Clojure. And I often get asked, why did you choose Clojure? This non-mainstream Lispy odd language? And I could answer things like, yeah, I mean, we do data analysis, and Clojure is actually great for data analysis, which it is. But that's not the reason we choose Clojure at all. In fact, it wasn't even a technical choice. The reason we choose Clojure was because I thought it looked fun. I wanted to learn the language. And I think that fun is a much underestimated driver of design. In fact, fun is a much underestimated motivator in the software industry, because fun is virtually a guarantee that things get done. So if you maintain a large code base, always remember to keep the fun into it. And I mean, even if you're locked down in your choice of technology or languages, there's always a lot of supporting code to write. So the next time you're faced with a boring, mundane, repetitive task, automate that task and do it in a language and technology of your choice. Turn a boring, repetitive experience into an exciting learning journey. Your code is going to thank you for it. So I'm almost done now, and before I leave time for questions, I just want to give you some links if you want some more details. If you want to know where the hotspots are in your code or how your temporal couples look, please have a look at CodeScene.io, which is all these analyses as a service. And it's completely free, so just sign up and play around with it. And if you want to explore all these analyses in more detail, I've written a whole book about it called Your Code is Crime Scene. And the good news are you don't even have to buy that book because you can win it here today. And you can also check out my blog at ampere.com, where I write a lot about this stuff and show you how you can use this information to your advantage to write maintainable code. All right. So before I take the questions, I want to take this opportunity and say thanks a lot for listening to me. And please remember that Common Lisp is a great language. Thanks. Whoa!
Oh, okay. Yeah, surprising. You talked before about maybe files being stable mean that we shouldn't touch them, but then you talked about inactive developers leaving. So it might be because the person left the project, but it might be just because the code is good enough and like REPL is going to change. So how do you resolve the two paradigms?
You obviously need to look at both of those dimensions. So I found that in particular, I use the hotspots a lot. That's the reason I started to develop them, because I was faced on almost a daily basis with the task of prioritizing improvements in large-scale software projects. And I found that so incredibly hard to do, and I often made the wrong choices. So we wasted time on improving something that didn't matter. So that's why I thought that if we actually look at the way we work, we can use that to our advantage and actually prioritize things based on how we have worked with the code so far. Because the past is often one of the best predictors of the future. So the other question is, with the knowledge loss, is something I've found that it's not so useful to do a knowledge loss analysis after the fact. You can use it, as I showed you, as a risk mitigation. But I find that the knowledge loss analysis is most useful when you do it as a simulation. So let's say you're a tech lead and someone decides to leave your project, or you pull them out and put them on another project. To run a simulation like that and identify which areas of the code have I been working in is quite useful. Because we tend to forget that. I mean, I've been leaving a lot of companies, and each time I left, I always forget them to tell about that little stuff over here in the corner that I also used to work on. So I think it's most useful as a simulation. Hope that answers your question.
Yeah, definitely, thank you.
Thanks. We have one more question over there. Wow.
What instruments do you use for such code analysis? Just because of there are too many possible problems. It's auto-generated code, it's binding between unit tests, it's binding between various features files when you change controller, view, model, etc., etc., etc. So which instruments do you use for this analysis?
So I actually, the tools I use are, I actually use CodeScene myself to do all that stuff. And I also, when I wrote my book, Your Code is a Crime Scene, I also wanted to make these techniques available for every reader to try out. So I wrote a small open source library called CodeMath that I deliver together with Your Code is a Crime Scene. You can find it on my GitHub page, which is capable of doing some of this stuff. And I find that the hard things with the analysis isn't to do the actual, I mean, it's a lot of work to implement the tools, of course, but the hardest part is to know how to interpret that information. And how you interpret that information depends on your context. It depends upon the challenges you face. So the way I do it in general is that I always tend to look at the hotspots, because they normally communicate something for me. I should be quite familiar with the top hotspots. And I've also found quite often that the organizational problems, with the scale of an organization, the organizational problems are always the one that you should address, but that's also the hardest part to address. So just to give you an example, 6 months ago, I did an analysis of a fairly large project, and they told me that they have just switched to feature teams. So they now had 12 different feature teams working on the code base. However, the code base was developed by a single team. There was nothing in the architecture that actually supported 12 different teams working in parallel. So as a consequence, their hotspots were on a daily basis modified by 12 different teams. And they were modified for different reasons, because they implemented different features. And that quite often led to a lot of problems. So they had this problem with different interactions between different features that they didn't expect. They also had this problem that the developers complained a lot that the code was so hard to understand. That was not because the code was bad. That was because it was impossible to build a stable long-term model of how the system worked, because it changed all the time by different programmers. So let's see, we should have time for like one more question. I'll be hanging around the whole day, so just catch me later.
I'll throw the box. Ready to catch the box?
Hi.
Hi.
Oh. So thanks a lot for an interesting presentation. What stuck to me is your last point about making it fun. So I guess everyone agrees that it's cool when it's fun, but at the same time, we are not doing things for fun. It has to be effective. Well, not only for that, or that not being the number one priority. So my question is, where do you draw this line? Because it's easy to justify a lot of things because they're fun to do, but it has to be, proper reasons. It must be effective, it must be productive, because 2 months in some technology switch, which may have looked like a good idea before, you have spent 2 months, and it's now kind of too late to switch back, and you're deep down, yourself.
Yeah, and that's of course the tricky part. I mean, the way I solved it was that I made my hobby into my day job. So I used to develop these software analysis tools in my spare time, and then I launched a startup to do it instead. But before I did that, I used to work as a software consultant. And this is a bit tricky, right? Because someone else pays me to do some specific work. So the way I did it was, and I think there's really no way around it, right? We need to invest some of our spare time into developing ourselves, into learning new stuff and exploring new stuff. So what I had been doing was that I had been teaching myself Common Lisp. If you haven't heard about it, look it up. It's a great language. But there was this project that we worked on, and we kind of needed some kind of test simulator. And it hadn't been planned for. There was no one available that could do that job. And besides, there wasn't enough time. So I said, oh, well, I can do that test simulator in like 1 day, because I had Common Lisp, the secret weapon. So I hacked it together in Common Lisp and became the hero of the project, and I got to use Lisp on a commercial project, and nobody cared what kind of language that was. They just wanted the functionality there. So look for opportunities like that. But in order to take those opportunities, you need to have the background knowledge. So this is something you need to build continuously over time. Perhaps by visiting conferences like this. That's a great opportunity. So I'll be hanging around for the rest of the day. Please just approach me. I'll be happy to discuss this. And if you want, I also have one of my final batches of Code as a Crime Scene stickers here. So please come and grab some stickers. And once again, thanks a lot for listening to me, and thanks for all your wonderful questions. Enjoy the day.